As a Japanese housewife living in the US, I want to look at the counterfacts of socialization from unique perspectives.
Et verions come back. Remember those old pictures of cities like Los Angeles or London, just completely choked in a thick, brown haze? That was smog. For decades, it was a symbol of industrial progress, but also a deadly killer. We fought a war against smog, a long, difficult battle for clean air. The air in many of our cities is dramatically cleaner than it was 50 years ago. But what if I told you that in our victory, we accidentally created a new, invisible enemy? This is the story of how our fight against one type of pollution inadvertently made another kind worse. Let's travel back to the mid-20th century. Post-war, industrial booms were in full swing. Factories churned out goods, and cars flooded the streets. But all this activity came at a price. The skies over major cities grew dark with pollutants. This wasn't just ugly. It was dangerous. People were getting sick. Respiratory illnesses soared. The infamous Great Smog of London in 1952 is estimated to have killed thousands in just a few days. It was a wake-up call. Scientists quickly identified the main culprits. One was sulfur dioxide, mostly from burning coal. But the bigger problem, especially in sunny, car-centric places like Los Angeles, was a nasty chemical cocktail. Sunlight was baking a soup of pollutants from car exhaust and industrial emissions, creating what we call photochemical smog. The key ingredients: volatile organic compounds, or VOCs, and nitrogen oxides, or NOx. So, the battle lines were drawn. Governments around the world, spurred by public outcry, started passing clean air legislation. The U.S. Clean Air Act of 1970 was a landmark moment. It set strict limits on emissions from both factories and vehicles. Automakers were forced to innovate, leading to one of the most important environmental inventions of our time, the catalytic converter. This little device, installed in the exhaust system of your car, is a miracle of chemistry. It takes harmful gases like nitrogen oxides and unburned hydrocarbons, which are VOCs, and converts them into much safer substances: nitrogen gas, carbon dioxide, and water vapor. As catalytic converters became standard on new cars, the results were stunning. Levels of NOx and VOCs began to drop dramatically. The thick, brown smog that once defined city skylines started to recede. We were cleaning the air, saving lives, and it felt like a total victory. But air chemistry is incredibly complex. It's like a giant, invisible puzzle where moving one piece can change the entire picture in unexpected ways. And that's exactly what happened. While we were focused on that visible, ground-level smog, we didn't fully realize we were altering the recipe for another pollutant, ground-level ozone. Now, hold on. You've probably heard of the ozone layer, high up in the stratosphere. That's the good ozone. It acts like a planetary sunscreen, protecting us from the sun's harmful ultraviolet radiation. But ozone can also form near the ground, where we live and breathe. And down here, it's not a friend. It's a major air pollutant, the main component of modern-day summer smog. Ground-level ozone isn't emitted directly. It's formed through a chemical reaction, a bit like the smog we were trying to get rid of. It needs two main ingredients plus a catalyst: VOCs, NOx, and sunlight. Sound familiar? These are the exact same pollutants we were targeting with catalytic converters. Here's where things get weird. You'd think that by reducing both NOx and VOCs, we'd reduce ozone too, right? Not exactly. The relationship between these chemicals is not linear. Imagine you're baking a cake and the recipe calls for flour, VOX, and sugar, NOx. In some situations, especially in urban areas with tons of traffic, there's a huge amount of sugar lot of NOx but a limited amount of flour, the VOCs. In this VOC limited environment, the amount of cake you can bake is determined by how much flour you have. Our war on smog was great at getting rid of some of the flour, the VOCs, from car exhaust. But here's the crazy twist. Nitrogen oxides, the NOx, don't just help create ozone, they can also destroy it. One of the gases in NOx is nitric oxide, or NO, freshly emitted from a tailpipe. Nitrogen monoxide can react with ozone and break it down. Think of it as a chemical Pac-Man gobbling up ozone molecules. So, in the past, right next to a busy highway, you had tons of NOx being pumped out. The NO part of it would immediately start destroying any ozone that tried to form. This created a little bubble of lower ozone right where the pollution was heaviest. But as we put catalytic converters on cars, we drastically cut NOx emissions. We took away the ozone-destroying Pac-Man. Suddenly, the chemical balance shifted. With less nitrogen monoxide around to scavenge it, ozone could stick around longer and build up to higher concentrations. We had successfully cleaned up the primary pollutants, the NOx and VOCs, but in doing so, we had removed the natural off switch for ozone in certain areas. The result? In many urban centers, while the hazy brown smog cleared, invisible ozone levels actually started to rise. We solved one problem and accidentally made another, one worse. This doesn't mean the Clean Air Act was a mistake. Far from it. The reduction in smog, acid rain, and pollutants like carbon monoxide has saved millions of lives and prevented countless illnesses. It's one of the greatest public health successes in history. But it highlights the incredible complexity of atmospheric science. It's a lesson that environmental solutions are rarely simple. So what's the situation today? We're now in a different phase of the clean air war. The focus has shifted more specifically to tackling ozone. Since we know ozone formation can be either VOC limited or NOx limited, depending on the location and time of day. Scientists are developing much more sophisticated models. Instead of a one-size-fits-all approach, regulators are creating targeted strategies. Insomarias, that noun VOCs from sources like industrial solvents and gasoline evaporation. In other areas, particularly downwind of cities, the focus is now on further reducing NOx. It's a much more nuanced fight. We're looking at everything from power, plant emissions to agricultural sources, and the challenge is global. As developing nations industrialize, they face the same air quality battles that Western countries did decades ago. But now, with the benefit of our hard-won knowledge, the story of smog and ozone is a perfect example of the law of unintended consequences. It shows us that when we intervene in a complex system like our planet's atmosphere, the results can be surprising. Our victory over the visible smog was real and vital, but it also revealed a hidden, more stubborn challenge lurking in the clear air. The air looks cleaner, and in many ways it is. But the invisible threat of ozone reminds us that the fight for truly clean, healthy air is never really over. It just evolves. Thanks for watching. If you found this dive into atmospheric chemistry interesting, give this video a like and subscribe for more stories about the science that shapes our world. See you next time.